Today we are talking about lectures 1 step for Unit 3 basic data structure. Let's review what we have so far in this course, problem solving with algorithm and data structure using Python. So let's look at the website. We actually so far only touched 2 lectures, 2 chapters. For chapter 1, we talk about the introduction about algorithm and data structure. Chapter 2, we talk about analysis, the complexity analysis so far, and basic data structure. So these 2 chapters, basically, we talk about what is data structure and what is algorithm. And then the purpose of using Python, is actually Python is easy to write programs. So in fact, we are trying to use Python as a pseudocode. So whatever data structure idea or algorithm idea, you can use Python to write it. And it will be fast to do prototyping. But the problem with Python is slow because fully object-oriented, and also it depends on the interpreter. It's not really machine code. So Python has its own limitation. So later we need you to use C++ to actually accelerate your program. But C++, each unit, you probably spend 2-3 days to do that. So we probably will finish the whole program using Python as top level, but some of the key functions we use C++ to do that. And then there is an interface that can connect Python to C++. It's called Swig. Swig is the interface that can connect two together. So that's why we use Python in this data structure course. And in the future, we may use that Swig interface. So let me give you a brief overview of, a short introduction of what is the Swig. So here you can say type Python Swig. So there is some Swig tutorial you can find. So there is Swig organization. And here you will say that it's how to run Swig and then have that C++ wrapping, how to wrap them up into Python. So here in the internet, you can find full description of Swig and Python. Okay, and Swig is only a module in Python. So actually you kind of can find a lot of information about Python, Perl, and a lot of things connected with Swig. And then your C++ can be used to actually speed up a lot of programs. So that's what we actually want to do. We have a Py program and then how to connect it with the C. Okay, that part is one of the purpose that we use Python as a driver or a script language to drive C program. And then that's one thing why right now we are using Python as a pseudocode for data structure. So that's why we use Python as a pseudocode. But the real data structure we will be using to speed up maybe C++ or Java. Even Java can speed up Python. And then Java is used for website construction or your whatever so-called the Android Studio for cell phone. Okay, and C++ you can go to game engine or something like that, programming. Okay, so that has different purpose for doing programming. But Python is a language that helps us to speed up Okay, that's one thing you need to know, that why so far we use this course for our data structure study. And chapter 2, we talk about how efficient a program can have, and we talk about basic data structure in Python like list. And we also have set. We also have dictionary and tuple, right? And these different things in our C language, you would have the so-called struct, the so-called pointer, the so-called class, vector. Okay, and then you have union. Okay, these different things. Okay, and then this list dictionary, tuple, different things actually can be used to implement this chapter 3 stack, queue, DQ, and then other things like list, array list, and then map, and then set, different things. And this whole thing, as you may have learned, this whole thing is called collection in Python, right? And then on your C side, you need to use this to implement, to realize this different data structure. So that part is your ICS 45C, and some part of ICS 46 will be covered in this, how to implement all of these. And in fact, your ICS 45C already implements string, array, and the linked list for these different data structures. So that's what we trying to do right here. And in this chapter 3, unit 3, basic data structure, we are talking about stack, queue, DQ, and then order list, that's a linked list. And then later we have recursion. Recursion is like we already know quite well. Sorting, searching, but know quite well. And then chapter 6 for tree algorithm is you have not touched yet. And chapter 7, graph. So basically here are more abstract data structure. So on top of your Python data structure, we have list, set, tuple, these basic data structures, dictionary. Okay, C, you have this struct, pointer, and then you have class, you have array, you have vector. These are the basic, we call it basic ADT, abstract data type. Okay, on top of it, it's the second level. We have stack, queue, DQ, and we have map. We may have dictionary actually also in this level. In fact, set and map and dictionary, whatever. Okay, that's the second level. And on top of it, we continue to move up. There's another layer. You would have tree, right? You have graph. You will have associated memory. Okay, this different level. And then in all this level, you may need to deal with the older one has a bracket for older one, and then redirection for toString, those different functions you need to implement. And you also may have to override plus, minus, or multiply or compare in order to calculate how many steps of the operation you need to have. So here in this level, we need to discuss those different topics to support you to study this QDQ map or higher level tree associated memory. And this topic we are going to cover upper level, including analysis of efficiency, is the main topic for data structure. And the application of this data structure is called the algorithm. Okay, and the algorithm, you have a course 146, and this one is 46. Okay, but sometimes these two courses is not really that well separated or differentiated. Is that okay so far? Hello? Hello? Is that okay so far? Hi, I don't hear you.
Hello?
Yeah, do you hear me?
I hear you, but I don't know why you don't hear me.
Yeah, probably you stay too far away. I know you are talking because I hear over here.
No. I'm right next to my mic.
Oh, okay.
My mic's
Something.
working. Your ear's not working. I don't know why.
Oh, okay. No,
Because it's
but,
like
but it's
fluctuating.
so far okay that I'm trying to tell you what is course 46 you will have, and then what is
Yeah.
146 you will have. So the purpose of having this one right here we are discussing is actually you will learn the pseudocode for data structure, right? And later on, you will need that idea in order to help you to develop a C double plus version of data structure in CS46. And then in US junior year, there is a CS 146 for algorithm. Okay, so this one is quite important. So learn Python for that. Okay, and now I'm going to give you a very small example to help you to understand why this data structure is so important. So here I have this one's there. So here, let me actually start a new program. Okay, start new program. Okay, so here I say from PyLab import star. Okay, so I'm using PyLab. Okay, I'm using PyLab. So I can have A equals 1, 2, 3, 4, right? And then B equals this, right? And then I say figure, right? And then show. Figure and show are a pair. This one is in MATLAB. It's not really for Matplotlib of Python. No, this one in MATLAB. It's a MATLAB function, and PyLab actually mimic MATLAB. Okay, so this one is you can do plot A and B, and then color with red. Okay, this one is very simple. So what I'm trying to say here is, oh, I'm sorry, the command is, I'm using the C Java as a command line, sorry. Okay, so you see this one actually is a x squared, okay, but it's only with number, it's not a smooth chart. But why I'm talking about here with this is actually, let me use a smaller one. Why I'm talking about this is like, I have a list, right? And I use that list for S square. So I create S square list, okay, and then I draw a chart that based on the S square chart. So this list are data structure. Okay, we do some computation. So we have core program doing some computation using this program Python to do that. And then outside, I use Pylab to help you to do visualization. Is that okay? To help you do visualization.
You hear me?
Yeah, I hear you. Yes.
So through the mic or through outside?
Through the mic. Yes.
Okay.
No problem. So here you actually have the core computation. Everything right now is called data structure. Outside, you can use Pylab to do that. Or if you are doing game, you have Pygame. Pygame is actually outside. Okay. Pygame is another one that actually is outside. It's also called Pygame. So these few things, and then are so-called GUI of some sort. Okay, graphic user interface. This one Pylab can be also viewed as a graphic user interface, and also you have the TK Inter. Right, TK Inter is another set of user interface. So in Python, you need to learn core computation, and you also need to learn the GUI. And as a whole, you can use the whole package to do problem solving, to do real projects. Okay, and now we are on the core computation for data structure. And later, you still need to learn those mathematical packages and Pygame and TK Inter that will help you to set up everything. And then your C language, because of Swift, can be driven by these interfaces to help you to realize those computation and be able to demo your project idea. Is that okay so far?
Yeah.
And also, actually, C language also have the OpenGL or some other tool can help you to do visualization. So from time to time, I will try to teach you something like this Pylab as well. So is this Pylab easy or no? Hello? Hello? Is it Pylab acceptable to you or no?
Yeah.
So basically, this plot is just to throw your A and B into your plot, right? And it automatically will give you the A versus B chart. Okay? It's not hard. Okay, so this part is not hard. Okay, that's the first demo program I have right here. So now let's go back to chapter 3. So basically here we are going to cover a few basic data structure, stack, queue, and a lot of things. But these different stack, queue, or list, or DQ, they are implemented by list actually, and it's not really that hard. Okay, so let's get started for this basic data structure. And then from next week, previous week I only cover chapter 1 and chapter 2. So we pretty much spend a few weeks, but we cover very little on them. We only cover chapter 1 and chapter 2. And now we need to speed up. So from next week, Monday, Wednesday, still 10 a.m., I will cover one lecture on this data structure. Okay, and then your Tuesday, Thursday, still 10 a.m. I try to cover C, but C is going to finish. And then we still have a 6 p.m. one that I will continue C double plus. So all of this is trying to help you get better understanding of what 46 will be doing. Okay, that's my plan so far, to help you to go into those topics quick and get more understanding. And 46 is actually very difficult because you need to be good on both data structure idea and also implementation using C double plus. So now let's get started for data structure step. But don't get frustrated or scared. These stack queue, DQ lists are all very simple one, and using Python is just a piece of cake. It's actually not that hard. So now let's get started. This chapter we will talk about stack queue, DQ, and list. And in this lecture 1, I'm going to only focus on stack. So to be able to implement ADT, abstract data type, so we try to teach you how to implement abstract data type, stack queue, DQ, using Python, list, only using this. And in fact, it's not much different from list. Okay, to understanding the performance and implementation of linear data structure. Linear means 1D, so list is like this. It's 1D, right? That's 1D collinear, and array is also 1D. And 2D is like matrix or 2D array. That's 2D. And now we are talking about linear. And 2D usually we call it quadratic. Right? 2D usually we call it quadratic. So 1D we call it linear. And then we understand prefix, infix, postfix expression. These are related to the application. So these are the application for stack. And then you value the postfix expression, something, that's an application. So now let's look at what is stack. Okay. In the second part, that's the queue part. That's the next lecture, but not in this lecture. To use queue for basic timing simulation, to able to recognize problem probability where stack queue and DQ are appropriate for data structure. So you also need to know when to use stack, when to use queue, and when to use DQ. And in fact, these different data structure you can find it in either Java collections or Python collections. They all have these different data structure already. And for 2D array in Python, you can use NumPy. And multiple dimension array, you can always use NumPy to get the. They are already implementation. Okay, so here actually we just try to teach you how are they programmed. Okay. And to be able to implement abstract data type list, like linked list, using node and referred pattern. So another thing we need to learn is node and pattern. And in C language, I also will teach you how to construct a node for next, previous, and then you can connect the linked list or circle list, the linked list. Okay, something like that. That's something you need to know right now in C language and C++ language, and also in Python. And then to be able to compare performance of our linked list implementation with Python's list. Okay, two are different. One is using your own linked list, one is using Python linked list. Okay, what are the linear structure? I talk about it. It's 1D. So stack, queue, DQ. These are example of data collections whose items are ordered depend on how are they added or removed from the data structure. Once an item is added, it stays in that position relative to the other component, and that comes before or after it. So it depends on the order you add it in and where you add it in. And collections such as these are often referred to as linear data structure. So queue, stack, DQ, list are linear structure. And set is also linear structure, but actually set have no order. Dictionary, you can also think about it as a linear structure, but it has key and value. It's associated type data. So what are linear data structure? Linear structure can also be thought of as having two ends. One is called left and one is called right, and sometimes called front and rear. You can also call them top or bottom. Okay, so it's depends on which data structure you talk about. Sometimes you have the right and the left, you have the front and the rear, or you have something called your top or bottom. Whatever, it's just depends on data structure, and it has different name for this 1D data structure. The name given to the ends are not significant because you always can change that. what distinguishes one linear data structure from the other is the way the items are added or removed. So these different data structure, Q, DQ, state, basically the differentiation is the way you actually add it or remove it. So how you organize the data, well, it depends on how you add it in or remove it, okay? For example, a structure might allow new item to be added only at one end. Some data structure allow the item to be removed from the other end. And then array is also a data structure, but it can be random access data. So here, actually, stack Q, DQ, and list. Okay, these are actually so-called iterative data structure. So you need to use an iterator to actually access the data. But something like array actually is a random access. So array actually allow you to do like A of 10, I access the data A of 10. But QDQ, you only have to try to pick, look at the top, or actually you just like push your pop, the top of the tail. Okay, so these different data structure actually is like more like depend on the end to do operation. But array actually you have the random access. It's actually more flexible in terms of accessing the data. But array in insertion deletion is not as efficient. So in terms of which data structure you use really depends on how efficient that can help you to do programming. Okay, and what are linear structure? These variants give rise to some of the most useful data structure in computer science. They appear in many algorithms. So these different data structure will appear in different algorithms and can be used to solve all kind of problems, a lot of problems. Okay, so these are the linear data structure. Any questions so far?
No, not yet.
Okay, so here is a chart for different ADT, okay? Different ADT. So we have explicit linear ordering, okay? And something is implicit data structure, okay? What are these differences? This stack string QDQ list, these are explicit. Explicit means what? I have a stack, right? I push, and then I pop. So the data has a explicit ordering. That actually you know that which one I push in or which one I pop out, right? And this one is implicit. It's a priority queue. Priority queue means what? When I put data into the queue, it already has a priority. Say if I like, okay, I have a queue, but I put in the data according to their GPA score. So 4.0, 4.0, 3.9, 3.7, something like that. Those kind of queues, student sorted with that, we put into a priority queue. And then higher ordered student, higher GPA will be dropped for admission, right? Those kind of data is called priority queue. It's implicit because the order we don't know. It is not really follow the way you add the data into there. And but this push and pop, or you have a queue, you put into the front or get it, put it into the rear and get it in front of front, or push into the top, pop out from top. That actually we know which order it is. That's explicit linear ordering. And those data structure that actually have priority has no obvious ordering, or we call it weak ordering. Is that okay?
Yeah.
But they do have an ordering. So this different thing, we call it hierarchical ordering. That means it depends on the 1D, depending on where they sit. Okay? And then we have the dictionary, so we have the equivalence relationship, and then the partial ordering. So we have graph and set and map. Set here actually is dictionary. right? Dictionary, we have the associate memory, have key and value. So that key and value actually map to the data's relationship, right? But you can see like this array or this list, it actually is put in 1, 2, 3, 4, 5 as the number for key. Okay, so array in some sense is a specialized dictionary. It's just using the index as a key. Okay, in terms of computation, it's something like that. So here, this one is a good organization chart of how these different ADT are organized, and all of these are in data structure. Okay, all these are in data structure. So now let's go back to what is really the stack. Stack we talk about is push down stack. So actually we have a stack like this, originally empty, we have tab at here, right? And then we push in 3, and we'll put 3 in there, my tab move up for the next available one. Then I push in 5, I have 5 in here, and I move up my tab, right? And then the next one, I say pop, I pop out 5, so this one kill, my tab move down to here. And then the next one, I pop out 3, my 3 get out, and then my tab go back to here. Okay, that's called stack, right? It's called stack. But stack is very useful because a lot of things are using stack. And in your SIG B course, I talk about push down automata. Remember that one?
Yeah, I remember that.
Push down automata, right? We talk about the regular language, regular expression. That one is no recursion, right? No recursion. You cannot have item and then call in item again. No, this one is not allowed in regular expression. No recursion one, we call it regular language and using regular expression. The one with the recursion is called what? It's called context-free. Remember that? It's called context-free grammar. Right? And context-free grammar actually allow recursion, but one level higher is called push-down automata. And push-down automata allow stack. Remember that one? So that actually means that push-down automata will give you a more powerful computing than the one with context-free grammar only have recursion. Recursion means that you have a function called f itself, right? But push-down automata actually is able to implement all the recursive program because your f can call f itself. This one may be f of 5, and you call f of 3, and then you call f of 1. So all of the computation by context-free grammar can be realized by push-down automata that use stack, right? Because you always can do this. For example, I can write a program. I can write a simple program, say, like this one is called sum of n, right? I can do sum of n, right? This one is summation of I from 1 to n, okay? So like 10 will be sum from 1 to 10. So this one will be s equals 0, and then for I in range 11, right? Ending at the 10, right? 11, and then sum plus equals I, right? And at the end, what should I do? Return S. This one will give you a iterative version of having sum, right? That's one is summation of 1 to 10, right? Is that okay so far?
Yeah.
And this one actually is what? I use a for loop, right? I did not use the recursive. But I can also write a recursive version of sum of n, and then I say if n equals 0, right? Return 0 or return n plus sum of n minus 1. This one is recursive version, right? Is that okay? This one is actually recursive version. And recursive version actually has the stack to help you to push and pop and then doing the computation. So push func automata can solve whatever problem using for loop, right? Using for loop. And it will be done more nicely. So a lot of computation may be using these different steps to help you to solve it. Okay, so here stack is very powerful. Stack can be used for push down automata. Stack can be used for language translation. Stack can be used for language translation. Can be used for recursive program calling. Okay, it can also be used to do backtracking. What is backtracking? Okay, what is backtracking? Now let me explain the Stack's application for backtracking. What is backtracking? Backtracking means, okay, here you have a maze. Something like that, okay? So I have an electrical mouse, right? It will go like this. I have a mouse, robot type of mouse, okay? Okay, my access is right here. I'm sorry. Oh, I lost that chair. But based on those kind of maze, okay? In those kind of maze, I get into. I'm sorry. I'm moving this around. I'm sorry. Okay, my mouse keep going in here, right? But I may go to here. Oh, it's a wrong route. I need to back up. Okay, so those are backup paths. Actually, I can start put into my previous location. I put into a stack. So if some stack I have nowhere to get out, I can pop up until there is a new route I can go to. And going to here, okay, no way, I just pop up. So my stack, I can keep track of all of the position points. So each box I record some data, say X and Y in there for point. So this one say 0, 0, this one say 1, 0, 2, 0. So I push in 0, 0 in, 1, 0 in, 2, 0 in, right? Something like that, and keep doing that until, okay, there is a one point I cannot get out, my mouse cannot get out. So I pop up to some point. Oh, I found a new route. Okay, that one I can go. Is that okay? Hello?
Mm-hmm.
Is that okay? So if this map, this maze map, I put every location for a certain index location, right? And I keep going, and to a certain point, I cannot get out. Okay, pop out those whole point that I don't have. Pop out those different point that I don't have way to do. Okay, here I end up to here, right? I pop out everything into that corner, and here back to this point, I have some new route to go. because at this point actually I have this one and this one to go. So I go this one. Go this one, so I keep pushing my location into my stack, right? And I have no way to get out. So I pop out to back to this point. This one already be used. I only have one way go out, okay, here. And then pop out, oh, there's no way. I go here, go here, go here, go here. Until I back to here. And then say here, try, oh, no way, I'll go back. You know what I'm saying? That actually you can do using stack. Okay? That actually you can use this stack. Or sometimes I have different game. Say I have a chess game. Right? I have my chess game, whatever my chess game it is. So I have A, B, C, D, E, F, right? Whatever 1, 2. And I also have this one, sorry. Let me write it in different location. 1, 2, 3, 4, 5, 6, 8, right? Okay. The first one I say I can do this one I move to here, say my A, B, F, G, whatever, my F. So for example, my F1 move to my F3, right? Whatever. Okay. And then you put this into a step. So I remember every step I move and the opponent's step they move, right? And then you keep track the different chess stone moving around the whole board, right? Now, okay, I want to do backtrack. So I pop out one of them, kill that one, restore whatever stone it is. You know what I'm saying? And here you may need to keep track of what stone has been removed as well. But by doing that, your stack can keep track of whatever move you have already done to the chess game. So stack can be used for backtracking. And then, okay, conceptually you think that, oh, that track may be so amazing and it may be too hard that I can implement. But in fact, stack is not that fancy when you implement. The stack can always be implemented by an array list or list. You know why? Because your stack always you can add or remove at the last one. And if you turn this one 90 degrees, it actually is a stack. So array list, the last one, add or remove right here. It actually is a stack. So you just need to use array list or Python's list to implement a stack. And you just put in those location call into an array list. You can basically backtrack in your chess game. Is that okay?
Yeah.
So stack is conceptually is a stack, but implementation is not fancy. It's just an array, or it's just an array list, or it's just a list. Conceptually it's something new, but implementation wise, it can be as simple as a list. Now let's look at the code. Okay, let's look at the code. Let's look at the code. So let me actually show you what it is. Okay. So here, say I have a stack, right? This one is a stack. Stack have the initialization. Okay, initialize my stack to a empty list. So I have a list called items. So my item is empty, right? Check if empty. So if the list equal to an empty list is an empty list. Okay, push. I append my item to my items. So just append to my current location. No matter where it is, my current location. Pop out, okay, I get the data from the last one. So this last one pop out. Okay, size, okay, I return the current list size. That's it. That's already a stack. So actually stack is nothing more than a stack is nothing more than a list. Nothing more than a list. It's just an application for list. Same thing if you are in C language, you can have a linked list to implement stack. Like using the structure, whatever, to implement the stack. Or you can simply use an array is good for list. Array is also good for list. Vector is also good for implement a list. So in C, C++, you have tons of different basic data structure to implement stack. Is that okay?
Yeah.
Is this hard or not hard?
It's okay.
It's okay, not too hard, right?
Yeah.
But the hard part is in the application, not really in the implementation. Implementation is just like this, nothing more. The class stack is just this, nothing more than that. Okay, nothing more than that, nothing more than this. Just these few lines is already a stack. Now I have a main program that initialize a stack. First, I check whether my data is empty or not. Okay, then I push for, push stock, picker should pick this stock, then push through, and then print out size empty 8.4 whatever. Let's run this one, okay, and then see the result. Okay, so the first one I push in 4. So actually I push in 4. I push in a 4 in there. I push in a dog in there. Right? Oh, the first one I check if it is empty. It's empty, so this one is empty. And then I pick whether the pick it or I pick it is showing the top. That's a dog. And I push through. Okay, I push through into there. I push through into there. And I check size. Size is 3. Now it's 3, so I got a 3. And then I check is empty. Oh no, this one is not empty. And then I push 8.4. Okay, I push 8.4. And I pop 8.4 out. So print my pop is actually 8.4. And then okay, print my pop. I pop out 2. So pop out 2. Okay, now my size 2 now. Okay. So if you trace this program, it's not that hard. Is that okay? Is that okay so far?
Yeah.
Okay.
Yeah.
So not really hard. Okay, stack is not really hard. It's actually nothing more than this. So your stack you can do push, pop, and pick. Pick means P-E-E-K. P-E-E-K. Pick means picking the top one, but you don't actually pop it out. Pop is like you pop out, get the data out, and the return value is actually the one being killed. Pick is not destructive. So this one is last in, first out. Okay, the one last get into the stack will be first pop out. So the one we do is this one, okay? And then, so if you keep pushing and then keep popping, you push everything in there and then you pop in, it will give you the reverse order. So push 4, push stop, push 2, push 8.4, then pop out 8.4, pop out 2, pop out dog, pop out 4. So the order you pop out actually is a reverse order of the way you push it. So stack have the function of reverse order. Is that okay? You can do to reverse the order. Is that okay? It can be used to reverse the order. So say right here, in this demo program right here, I actually I write a new program called stack, right? And right here in this stack program, let me just copy this stack over to here, right? And I save. I save this one, save all, okay? And right here, I new a program called reverse. Okay, I knew a program, so from stack, import everything, okay. I can just import stack, okay, just takes nothing. So right here, actually, I can set a original list equals 1, 2, 3, 4, right? And then 4, and then I say S equals stack, right? And then for I in range of length of original, right? And then S the push of original of I. Okay, I'm sorry. Should be then go back to I, right? And then new equals empty one, right? And then for I in range of S dot size, right? Stack size. I'm sorry, it shouldn't be this. This should be still be range of, your size will be changing, okay? Length of original, right? And then I have new dot append of S dot pop. Okay. Okay, now I do this. Here I say print original. Okay. And I say print is that okay?
Yes.
So
Yes.
every time I push my data from original, one item from original. So what happened is like my list, I have 1, 2, 3, 4, right? So I push this one into a stack, and then push 2 into a stack, push 3 into the stack, push 4 into the stack. After I finish everything, I pop out 4, add into a new, pop out 3, add into a new, pop out 2 into a new, pop out 1 into a new. So the order now should be in the reverse order of the original list.
Mm-hmm.
Is that okay?
Yeah.
So now that's wrong. So one of the feature of the stack is to do reverse. I'm sorry, what's that? Interpret original. Did I wait? Range can. What's wrong with that? Length or original? Do I type something wrong or ORIGIN? For I range RANGE object cannot be interpreted as an integer. Wait.
Huh?
Do I make a mistake on here or no? For I equals, wait. Oh, here, this one. I'm sorry, I typed it. Double pilot, I'm sorry. Okay, I'm sorry. Okay, I made a mistake over here. It's this one, not the first one. I'm sorry. Okay, that's wrong again. Sometimes type too fast and then did not look at it. Okay. So as you can see, backtracking is also a reverse order, and this one is reverse order. But stack is more than a reverse order because it can be do reverse order at certain time. You just pop out a certain part and you can push in new, and then you can do something more and then pop out. So actually, stack is more like a tree structure. It's more than just a reverse. Reverse is like do the whole thing in and then pop the whole thing out is reverse. So tree is something like you can try here, and then backtrack. Okay, here, go back, try here. Okay, go down and then go back. Try this. So stack is more like a tree structure.
Uh-huh.
You know what I'm saying?
Yeah.
More like tree structure. And if you reverse this chart, bottom up, it will be something like this. It will be something like this. You know, your stack will be something like this. The data order will be something like this. Okay. fork it like that. Okay, that's the stack. So it is give you a good picture for stack or no?
Yeah.
Are you okay to understand what stack is? So
Mm-hmm.
stack in terms of implementation is nothing more than an array or a list or a vector in C++, or that's just a linear data structure. But when you use it, it's actually quite powerful. But the main function you need to use is like push, pop, and pick three data, and then you can create a stack, push, pop, pick, and then it's empty and size. Okay, we see that. So here we push in those different data in there, check in empty, pop, 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 and check size. Okay, that's the one we see in the previous function. Now let's see how to implement stack in Python using this. So you can use an array for stack implementation, or you can use linked list. Okay, when you use an array to implement that, you actually using index for doing that. Okay, you use the index to doing that, and you can use the list, but this actually is easier to use. So primary collection, Python, as in any other object-oriented programming language, the implementation choice for abstract data type, such as stack, is created in as a new class. The stack operations are implemented as methods in that class. So we talk about that. Further, to implement stack, which is a collection of elements, it makes sense to utilize the power and simplicity of primary collection. Primary collection means what? Means list, set, tuple, and dictionary. Okay, the primary. And I'm sorry. Okay, and then using primary collection, we call that the list class in Python provide all the collection. And if we have the list 234, 23, 253, 674, we need only to decide which end of the list you will be considered the top of the stack. So usually the tail, the top, the top side, the end of the stack is the top. That would be easier. Once the decision has been made, appropriate operation can be implemented using the list method such as append and pop. So append and pop are used for that. So the demo program is shown in stack. So our stack, I already shown it. The stack function, I already showed it. It actually using push and pop. Push and pop from the list itself. Okay, so push and pop actually is append and pop in Python's list. So Python list is actually quite powerful in terms of using for those purpose. So don't get scared, right? This part is not too hard for stack. And then stack class, we talk about it. The next one, we already shown it in the demo. And then here has a stack 2. Stack 2 program, here the stack is the same, but this one peak. And the only difference in the stack 1 and stack 2 is this stack 2, we're not using the tail part. This one is using append and pop, right? Instead of using that, I'm using the 0 location as my top. So every time I insert to the 0 location. Mm-hmm. And when I pop from the 0. But this, I think, is a stupid way to do it, okay? This is a stupid way to do it. Because this will be costly, because when you insert here, everything need to be pushed down. That one is costly in computation. Mm-hmm. Just showing here that the list can be used to implement stack in different way. Is that okay? Other than that, there is no much purpose. So the ability to change the physical implementation of an abstract data type while maintaining logical characteristic is an example of abstract at work. So basically, I had 2 versions of the stack 1 and stack 2. Stack 1 and stack 2. I implement the same function for this and this, push and pop and pick. Okay, same function that I want to implement, but I have the version 1 that's using this I have version 1, I'm using this N for push and pop. Version 2, I'm using this N for push and pop, using 0 or using ln en minus 1.
Mm-hmm.
The two versions. I think this version is better. To me, it's natural and better. But both way can be used to do this. Okay, now the discussion. However, even though the stack will work either way, if we consider the performance of two implementation, there definitely is a difference. Recall that the append and pop are both order of 1. That means that the first implementation perform push and pop in constant time, no matter how many items are in the stack. The performance of the second implementation suffered for insert and pop operation. Both of them are order of n because you need to, this one, when you implement this one from here to here, whenever you push your pop data, you need to ship everything to the right because list is actually implemented by array. So that's the stupid way to do it. It's an order of n operation. So that has no clear reason of why we need that step 2. Here we give it as an example just to say that that's a stupid way to do step. Okay, so this one, let's go to our online course. Okay, this one, let's go to the online course. Okay, this one, we have a program you can run. I'm not going to run that. We finished that. So this one, I'm going to do this one. This one, we have that hello and true. Okay, so basically we create a step and then we push hello, push true, and then pop out something. Okay, we just want to do this. Okay, let me minimize it. So I show this one just to tell you that on the website we have for this class, it had call and had demo program like this. So let's try to first step forward. So the first one, I create a object. Okay, I click forward. So I create a class, and then that it comes with a object. It comes with the object, so the object is right here, right? It comes with the object. Now I do the second step. So after that, I initialize a stack, and then the stack, it has an empty instance. So one more step. Okay, then I check. I assign an empty a empty list to it. Okay, then after that, I go to line 4. I go back to push hello. So I push hello into there. So I call push, and then I start to push data into the list. And then the next one, I finish the push function. I go back to here between 21 and 22, and I push true. So I call to push again, and then I push true into there. But here, because I'm inserting to 0, so it actually is this one, this example is a implementation by this. Okay, it's an implementation by this. So I insert that to the 0 location. Insert that to the 0 location, keep going. Okay, and then after that, I pop it out. Pop it out, I go to pop and pop out the location from 0. So the true got pop out. And then I finish the last one, I finish. Okay, and the pop out data is when I print it is actually true. Is that okay? And I show you how to use this. Now let's do self-check. Okay, question 34. Can you answer this question 34? Given the following sequence of stack operation, what is the top item of the stack when the sequence complete? After this sequence is complete, what is the top item? Top item is like the item that had not been popped out. The last one to be popped out, but had not been popped out. Can you draw a chart to trace this one and tell me what would be the top one of the stack?
Give me a second.
Use your pencil and paper to do it. So the good thing about this course, the online course, is that it also give you the demonstration, and it also give you this kind of self-check. Not difficult one, but doable one. Can you use pencil and paper and then tell me what?
Top. Let's see what's
You push X, push Y, pop, and then push G. What will be on top? Peak has no fun, right? Peak won't add or
Z would be on top.
Yeah, the top.
Z.
Yeah, Z. The answer is Z. Yes. Good job. Good job. Okay. Why is D? Because you have a stack. You push in X, push in Y, then pop out, right? And then push in G, and then peak. Peak has no harm. So the answer is G. Is that okay?
Yeah.
So this will help you to understand it. Let's try to check the answer. Good job, right? Okay, now this is 35. Given the following sequence stack operation, what is the top item stack when the sequence complete? Push, 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 while not empty, pop, pop, 2 times.
Push, push, push. What?
So you had G on top of Y on top of X after 3 push, right? Then while M is not empty, pop out 2.
Error? Or the stack is empty.
You pop one
Error.
extra pop, right? One extra pop would cause what?
Error.
If you pop from the empties, what will happen? Let's check our code. Okay.
Am I right or wrong?
I don't know. Let's check our code.
You don't know?
Our stack, if we actually pop from list with empty list for pop, what will it be? Pop an empty list, what will it be?
I don't know. I think it's either error.
Let's say it's errors. So you will be between B and C, right?
Yeah.
Yeah, it will create an error.
Yeah, because you can't pop.
You can cover empty stuff. Okay, good job. You're really good. Okay, you're really good this part for list and Python. Not actually, at least you already learned quite good stuff. Now let's go down to this one's implementation for stack, right? And this one, let's move on to the next section. It actually implements stack using array. Now that we would like to implement it using array. So array represent a stack. Array represent a stack. It's not too hard. It actually just having the index 0, 1, 2, something like that, right? So always has a top as an integer to point into the current location. But if originally set the array to be 16, once you overflow, you need to double the array size. You know what I'm saying? So the maximum size. Once you pass the size, you need to double the size of the stack. Is that okay? Or if you don't want to double the size, you need to check for overflow and underflow. Okay? Check for overflow and underflow condition. Is that okay? Using array, you only need to take care of that. Other than that, it's the same with list. So let's keep doing. So top is available. Usually you use an integer as top. And then you actually 0, 1, 2, something, and top keep track of the is an integer variable keep track. So whenever you move up, you top increase, or move down, you use a top decrease. And if the top is 0, you no longer can decrease. If top is a maximum, you can no longer increase. Okay, so that's some rule you actually in your array. Or when you are the top is actually max size plus 1 minus 1. That's already the top. You already full. That's the check-in for full or overflow. Second, implement the increment. and then pick is like this. Assign or pick, insert the element is assigned to pop, and then insert that. So this one's adding the element. So increase the top, and then you actually push in the data with the data. Okay, so that's that. So the next one, to delete, it actually decrease the top first. Okay, and then you take out the data. Okay, actually, I'm sorry. The first one, you check whether it's underflow or not, and then you actually every time you take out the data and decrease the element. Okay, so that's what it is. Now that's the array. That's nothing special. The next one is I don't want to spend time to implement that stack. Actually, we already did that in Java or some other program. So now the next one is a simple balance of parentheses. This one is to check whether you have this. This one is a balance parenthesis. Means every left parenthesis has a right one to match with it, but of different level. But say this one is not balanced. Okay, or this one is not balanced. Or this one is not balanced. Is that okay? So using state, you can check whether it's balanced or not. Okay, so what happens is like whenever you see this, you push. You see a this, you pop. Okay, so but if pop, you have nothing to be popped, or you have nothing to be pushed, then you will create trouble. Okay, so let's see this one. Let's see this one. We have this, right? First one I push, so let me have a step. First one I push this one. Second one I push this one. Then I see the third one, I actually pop this one. I have this one, right? I have this one, so I pop this one. Okay, I have someone to repop, so that's balance, right? So next one, I push this one again. I push this one again, and then I pop this one, so I kill this one, right? And the last one, I pop another one. I pop this one, and then my program ends. And when my program ends, I check my stack is empty. Then that's balanced. Then that's balanced. Is that okay? Keep focus on my stuff, okay? Keep focus on don't do something else. Don't do typing. I hear you clicking. It's not good. This one is actually not that simple. So now if I have a unbalanced one, if I have an unbalanced one, I push, right? And then I pop.
Yeah.
Because the last one I pop. I pop this one, and then the string ended. When string ended, the size is 2. No, that's unbalanced, right? Or if I say starting from this, and then I only do pop, but my tree already, my stack already empty, that is unbalanced. Is that okay? So popping from an popping from an empty stack, or I finish my string, and then there are still some left parentheses in the stack. That means it's not balanced. Otherwise, I use push and pop should be able to check whether my parentheses is balanced or not. And actually something in between actually is useless. Say I have this one. Right? All these things are useless. All these things are useless. Is that okay?
Yeah.
All these things are useless. The only thing I need to interpret is this. And then I push the first one in, I push the second one in, and then I see this one, I pop. I see this one, I pop. Okay, when I finish here, I finish everything. The stack is already empty. That's balanced. That's already balanced. Is that okay? So here is using stack to check balance. So simple parentheses. We now turn our attention to using stack to solve real computer science problems. We have no doubt written arithmetic expressions such as this, right? And then when parentheses are used in order to order the performance of operation, you may have some experience in programming language such as this, whatever. And then the definition of the function called square will return the square of the argument n. Okay, this is not important. Now balance parentheses. In both of the I'm sorry. Okay, both of these need a balance operation anyway. We just forget about whatever inside or outside the parentheses, and then we'll sum up with this kind of balance strings. Okay, then compare those with following unbalanced. These are unbalanced. And to check that it's not hard, we just, when we meet the left one, we push into the tree. Meet the right one, we pop it out, and then we check whether when we finish the whole string, there are still some residue left parentheses, then it's not balanced. Okay, or when we try to pop something out, but there's nothing to be popped out, that means that we have right parentheses that is unbalanced. Okay, two conditions you need to check. Okay, let's do parentheses checker .py. Is that okay, Eric?
Yeah.
Okay, let's do this one. Parentheses checker. Okay, this parentheses checker. So we import stack, right? So we create a stack. And initially we set balance to be true. Okay, so this one is a default true. Default it will be true. Once we meet this is default true. Once we meet something wrong, we will declare it. Okay. So now we while the symbol string. So actually we have symbol string. We keep using each index of one and it's balanced. We continue to do that. Once we know that it's unbalanced, we will get out. Okay. We'll get out and get the unbalanced. Okay, now each time we get a new symbol, we get a new symbol from here, right? We get a new symbol from here, and then if it is a parenthesis, we push it into there. Okay. Otherwise, if it is empty, Otherwise, if it is a right parenthesis, and then the stack is empty, that means that we try to pop something out, and the stack already empty, then it's not balanced. Once it's not balanced, we get out and return is unbalanced. Okay, and then if it is a right parenthesis and the stack is not empty, then we pop one thing out, and then we keep increase the index because we move on our index to the right, one by one checking. Okay, at the end, if it's empty balance and the stack is empty, it's balanced and the stack is empty, everything got pop out, then we return true. Otherwise, we return false. So this one will implement the two conditions for us. If we finish the whole string and then the whole checker stay balanced, then that is a balanced parenthesis pairs. And then if it is not balanced or at the end of the checker is not empty, that means there is residue left parenthesis left, then that is not balanced. So now let's check this one. First one is balanced, second one is unbalanced. Let's check these two programs. Okay? Is that okay so far?
Yeah.
So this show you the stack can be used for parenthesis checking. And parenthesis checking is very useful stuff because when you do some programming language, you need to check that. Okay, so the code I show you already. So basically, let me just talk about this one more time. Initially we set it to be default true. Okay, so when something make it unbalanced, we just explain it. So every time I traverse to my input stream, whatever, advance by 1. So each time I increase by 1. That means that I move to my next index. And here, each time I check whether it's left parenthesis, I push it into a stack. Okay, otherwise I try to pop it. Otherwise, if I have a right parenthesis, this is under assumption that the symbol only had this and this. Okay, and then otherwise I say whether if I try to pop it and then my stack already empty, I have the right hand side by stack already empty, then it's not balanced. So I actually set it to be unbalanced and get out of the while loop. You no longer need to check any more condition. And then this one will return false anyway. But if nothing like that happen, if nothing like that happen, I keep progressing to the right. And then at the end of the function, my stack is not empty. That means I still have more left hand side left. Then it's also not balanced. Okay, so 2 conditions to be checked, and then you will make sure that it's balanced or not balanced. So the next one is a more general case. A more general case means that you have curly brace, you have the bracket being added into here. Okay, so you need to, when you pop out, you need to pop out the same one you have. Eric, is that okay?
Yeah.
More general case means that the previous one is like, it's only left, right, check-in, right? But this time you push this, and then in between you have a lot of this, that's fine. When you pop out, you need to match this side. But don't worry about in between. In between, they have their own push and pop pair. Okay? And once you check it's not the right one you have, you pop out not the right one you have, it's actually unbalanced. So this one is unbalanced cases. This one is unbalanced cases, like this is not pair, right? Or this one no pair with it. This one no pair with it. Okay? When you pop out or the end of the stack, you actually have no one to pair with you, is pair, or you pop out something that's not pair with you. So that's the parity check number 2. Okay, that's a parity checker number 2. Let's look at the call. Now, it's the same thing. You get a simple string in here. Okay, so a simple string could be something like this. You get that in. Same thing. We use a default true. We traverse through a whole set of this and this, this and this. Okay, and then if it's in here, we push it in. Right? And then if it's empty, if it at the end of empty and we try, if the state already empty and we try to pop out something, that is still false. So this one's still true, okay? And then otherwise, if we see a right-hand side one, we pop it out. And we pop out and matching the symbol, so it should be a 1. The top should be the one we pop out should be the left hand side, and the one symbol that we currently reviewing should be the right hand side. 2 need to be matched, so we need to call someone called match. So someone called match. If we have this opener and the closer, opener and the closer's index need to be matched. What is that? Because the opener we have this one as 0, this one index 1, this one index 2, right? And then closer, this one index 0, this one index 1, this one index 2. So as long as the opener and the closer has the same index, that means they are same pair. Same pair, they will be matched. Is that okay?
Yeah.
Okay? Other than that, it's the same algorithm with the previous one. Okay, it said that this time we have 3 type of opener and closer. We need to do checking. And checking this one is 0, 1, 2. This one, and this one is 0, 1, 2. And 2 opener and closer need to be matched. The one we pop out is opener. And the one we currently traversing is actually the closer. 2 need to be matched. If it unmatched, it's not balanced. And same thing every time we increase the index. So other than that, this is the same with our previous parenthesis checker one. Otherwise, it's the same. It's a little bit more difficult, but still following the same logic we have. And then let's look at the parenthesis, the check-in number 2. Right here. Okay, and then it had this, and then that's wrong. So download this program, have fun, you run sometime with it. Okay, you should see this. Okay, now let's go to the next one. That's the parenthesis number 2. You should run it. Let me try to pull out the website. So that's the next one, parents tree, simple parents parenthesis. Now we're done with this. The next one we have parents simple general cases. It had a wrong program, nothing else, so it's done.
Okay.
Okay, so that's it for today. Thank you. Bye now.
Bye.